Warning, the video you're about to watch contains mathematics at the level of differential calculus, also known as Calc 1. All material has an assumed prerequisite of pre-calculus and a full semester course in trigonometry. A thorough review of prerequisite topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is the door to Calc 2. You are now experiencing Calc 2 from this point forward. Once you've passed the fundamental theorem of calculus part 2, you are now working on calculus 2 topics. So let's dive in. Prior to this, you should have watched the videos, or at least you should know about the fundamental theorem of calculus part 1 and 2. You should know how to use part 1, and here in this video we'll talk about how to use part 2. So here we go. Evaluate the integral. And remember, the fundamental theorem of calculus part 2 says the following. The integral from a to b of little f of x dx is equal to capital F of b minus capital F at a, where capital F prime is little f. That is, capital F is an antiderivative of little f. And by the way, this brings together derivatives and integrals and marries them into the same concept. They undo each other. Integration is the parent, and derivatives are the child in a way. You take a derivative to get to the child, you take an integral to get to the parent. One thing that must be stated here, f has to be continuous on the interval in question. So our f must be continuous between the lower and upper limits of your definite integral. All right, that being said, let's just try this out. So every time now that you face a definite integral like this one, you ask yourself, what would I take the derivative of to arrive at this integrand? Right there. And I keep trying to point at that, but it's just not working for me. Anyway, that guy right there. Now, if this is not a basic result of a derivative, then you know that you either are faced with a problem you can't do, or there's some algebraic manipulation. And as I've said throughout this entire lecture series, algebra before calculus, I happen to know that e to the u plus 1 is the same thing as e to the u times e to the first. And e to the first is just a constant. So I can factor that outside of the integral. By the properties of definite integrals, you can factor out constants. And so I have this integral from -1 to 1 of e to the u du. Now I'm going to start warning you of things I'll often see students do. One thing you should never forget, do not forget to write your differential. Because really what you're doing when you're evaluating integrals is you're finding areas under curves, and you need a function height and a width, a height times a width. And if you don't have the width there, then you're not evaluating an integral. Anyhow, what would you take the derivative of to get e to the u? In other words, what is the antiderivative of e to the u? It is e to the u, right? That's what you would take the derivative of. And so you would evaluate that e to the u at 1 minus evaluate that e to the u at -1. And this is the result. That's that value right there, which you could distribute e through this and you get e squared minus 1. That value is the area underneath e to the u plus 1 from -1 to 1. Look how clean, how fast that is. Now, as we move through, I want to introduce several types of notations to speed up or to help you kind of keep track of your integrations. Because you're not always going to want to write immediately from here to there. Often, you'll want to do something like this. E to the first times, well, the antiderivative of e to the u is e to the u. And you want to evaluate that from u equals -1 to u equals 1. That's a notation that we would use. This antiderivative is written in there. So you find the antiderivative of e to u, you write it in this block here. And then you write the limits of integration on the outside of that block to remind you of what you need to do next, which is evaluate that e to the u at 1 minus evaluate that e to the u at -1. Now I know what you're probably thinking. Why would I take that extra step when it was just as easy just to go right to here? Well, you'll see as the examples grow more robust that it's not always to your advantage to skip steps. You'll lose track of thought. So let's go ahead and see some bigger examples. Evaluate this integral. All right, so I'll start by saying, as written, I don't know what I would take the derivative of naturally to arrive at 1 over 4x. However, a little bit of arithmetic beforehand, specifically factoring out a 1/4, allows me to see that this is 1 over x that I'm trying to take the antiderivative of. And the antiderivative of 1 over x, and this is an incredibly important antiderivative, is the natural log of the absolute value of x. Not of x, but of the absolute value of x. That's critically important as you move forward. And we're evaluating this from x equals 1 to x equals 2. So let's go ahead and do that. That's 1/4 times the natural log. Now you don't need the absolute value when you plug in a 2 because 2 is already positive. So it's just natural log of 2 minus, and then evaluate the natural log at this lower limit. So it'll be natural log of 1. A mistake I'll often see students do is they'll leave that natural log of 1 there. You should know natural log of 1 is 0. So just like you would not tell somebody, oh, I have $5 plus $0 in my wallet, you would say I have $5 on me, right? You would not say plus 0, so you shouldn't say plus or minus natural log of 1 either. So this is going to just be written as 1/4 the natural log of 2. If you want to bring that 1/4 into the exponent of the 2 there, you're more than welcome to, but you don't have to. Also notice, by the way, when you're evaluating these are the areas under the curve, right? So if I were to draw out this curve, 1 over x, from 1 over 4x, from x equals 1 to x equals 2, it looks something like this. Okay, that's 1 to 2. And it's not exactly that, but whatever. And you have just found that area, right? That's what this constant is the area underneath that curve. Notice, unlike regular antiderivatives, we do not have a plus c here. And the reason why is because you're finding the actual value. You're actually finding the true area between x equals 1 and x equals 2 underneath that curve. There's no need to have a plus c there. It won't occur. Let's go ahead and do something a little more interesting. We have an integral, definite integral, from -3 to 4 of f of x dx. But f is a piecewise defined function. It takes on different values depending upon what x is. And because of that, I can use properties of integrals to rewrite this piecewise defined function as the following. I can integrate from -3 to 0, and the function will take on the value of 2 over that region. Plus, I can integrate from 0 to 4, and the function takes on the value of 3 minus x squared in that region. Now, I have mentioned previously that when you're faced with integrals, definite integrals, you would like to use geometry as much as possible. This, you could find the antiderivative and do all that stuff, or, and I highly recommend you get used to this, you could say, oh, I have a function, here's the x-axis, of height 2. That's y equals 2 right there. And I'm evaluating or finding the area underneath that curve from -3 to 0. Well, that width of that rectangle I've just shaded, it has a width of 3 and a height of 2. That integral will be 6. If you want to be very mechanical about it, you're more than welcome to do that. You could, I'm just going to pull it out over here, you could say, well, the integral from -3 to 0 of 2 dx, well, the antiderivative of 2 is 2x. That's what you would take the derivative of to arrive at 2. And you're going to evaluate this from x equals -3 to x equals 0. And so to evaluate this, you'd plug in the upper limit, 2 times 0, minus 2 times plug in the lower limit, -3. And so you get 0 plus 6, or 6. Notice the difference between the geometric method and the computational method. The computational method often requires more work. I find that doing geometry or drawing a quick picture really does help out, but it only is very useful if you have very simple geometry, nothing crazy, and definitely not with a parabola. I would go ahead and integrate mechanically with a parabola. So let's go ahead and do that with that parabola. In fact, you could technically even break this up into the integral from 0 to 4 of 3, and then minus the integral from 0 to 4 of x squared, but I'm not going to do that. With something like this, I just glue them together and I don't bother splitting that apart. So let's see, what would you take the derivative of to get 3? Well, if you said 3x, you're correct. What would you take the derivative of, or in other words, what's the antiderivative of, that negative x squared? Well, that'd be negative x to the third divided by 3, right? Add 1 to the power, divide by that new power. And you're evaluating that from x equals 0 to x equals 4. That's the antiderivative in here. And we're going to plug in the upper limit and then subtract off the lower limit. I shouldn't say subtract off the lower limit. We're subtracting off the value of that antiderivative at the lower limit. Well, at the upper limit, you get 12 minus 4 cubed over 3 minus, and then at the lower limit, you just get zeros. That's what's nice about having a limit that's 0, is that things disappear very often. But as if calculus wasn't already a little challenging for people, the problem occurs that there are two things that will be the downfall for a lot of students in a Calc 2 course. One will be missing parentheses and missing negatives. I see that all the time. When you subtract off the antiderivative evaluated at the lower limit, a lot of people forget to write parentheses in there. Remember, you're subtracting the entire antiderivative at the lower limit. And so if it's not 0, but something non-zero, like let's say 5 plus 1 or something like that, I don't know, then you're subtracting that entire summation, not just the 5. So lack of parentheses is one thing that often happens and causes mistakes in Calc 2. Another thing is there's a lot of heavy arithmetic, as you're about to see. It just is kind of arithmetic heavy. You just can't avoid it. So let's see, 18 is 30, 54. So that's 54 over 3 minus 64 over 3. That's negative 10 thirds. Oops, negative 10 thirds. All right. And that tells us the area underneath this curve that was handed to us is actually a negative area from -3 to +4. Oh, okay, I'll believe it. And away we go to this next example. Let's see here. We have the integral from 0 to pi/4 of 9 secant squared of t dt. First of all, I don't like constants inside my integrals if I can factor them out, so that's what I'm going to do. I'm going to factor that out. So that's the integral from 0 to pi/4 of secant squared t dt, and that was being multiplied by 9. Another thing you have to be very careful of with trig functions especially, specifically the reciprocal trig functions, are domain issues. Remember, the fundamental theorem of calculus part 2 can be applied as long as your function that you're taking the integral of is continuous on that interval from 0 to pi/4. Luckily, secant is continuous and defined on the interval from 0 to pi/4. But if we went from 0 to 2 pi, we'd have a lot of issues because the secant is not defined on every number between 0 and 2 pi. So be very careful with that. You cannot tackle those problems until you have more theory behind you. But now we're going to ask, what would we take what would be the antiderivative of secant squared? In other words, what did you take the derivative of to arrive at a secant squared? And if you said the tangent, you are absolutely correct. So I'm going to write it this way because I just want to showcase another type of notation that people commonly use. The antiderivative is the tangent of t, and I'm going to evaluate that at the lower limit of 0 and at the upper limit of pi over 4. Notice I'm not using brackets this time, I'm just using a pipe there. It's just another style of notation. You'll see, depending on your textbook, which one gets used the most. So this will be 9 times the quantity, the tangent evaluated at the upper limit, minus the tangent evaluated at the lower limit. You should already have a couple full semesters of trig behind you, so there is no excuse for leaving these as tangents of pi over 4 and tangents of 0. You should know tangent of pi over 4 is 1, tangent of 0 is 0, so this is going to be 9 times 1, or 9. That is the area underneath 9 times secant squared from 0 to pi over 4, which, by the way, is astonishing that it's such a nice number underneath a secant squared, right? I mean, isn't that pretty amazing? You're dealing with this function, the secant squared, which sort of looks like this from, and you're specifically doing it from 0 to pi over 4. So you're really looking at this area right here. And it turns out that's a nice clean area. Isn't that pretty rad? I think it's so neat. As our final example, it's just one to showcase that you need to do algebra before you do calculus. If you look at this, you have no clue what you would take the derivative of to arrive at that fraction. Therefore, there must be something you need to do first, and that something is called algebra. Do algebra before calculus. This is the integral from 1 to 9, and we're going to break it into two pieces, x over root x minus 1 over root x. And if you're saying to yourself, I don't know the antiderivative of x over root x, I will slap you. You need to do more algebra first, right? This needs to be written as the integral from 1 to 9 of root x, which I prefer to write as x to the 1/2, to be honest with you, minus x to the negative 1/2. And at that point, you should say, oh, yeah, I could totally find the antiderivatives of those. Because remember, the antiderivative of x to the n is x to the n plus 1 divided by n plus 1. In other words, add 1 to the power, divide by the new power. So let's go ahead and do that. The antiderivative of that first one is going to be x to the 3/2, add 1 to the power, and divide by that new power, which means multiply by the reciprocal of that new power. Minus the antiderivative of x to the negative 1/2, you would add 1/2 to its, 1 to its power to get 1/2, and multiply by the reciprocal of its new power. And we are evaluating these from x equals 1 to 9. So let's go ahead and do this. I'll plug in the 9 first, obviously, because that's what you have to do. So let's go ahead and do that. We have 2/3 times 9 to the 3/2 minus 2 times 9 to the 1/2. And then we're going to lose, start a parenthesis. Notice how I said that. Start a parenthesis. You want to start a parenthesis because if you don't, you're going to have a sign mistake there. And that's one of the most common mistakes in calculus. So group things when you're subtracting. So we subtract the group, which is 2/3 times 1 to a power. Doesn't matter. It's just 1. Minus 2 times 1 to the 1/2, which is 1. So there we go. Now clean this up. Don't leave it like this. You know how to do your, this is really technically arithmetic. Square root of 9 is 3. And that's being cubed still. Minus 2 times the square root of 9 is 3. And for some reason my screen is not liking me at this time. Minus 2/3 and plus 2. Remember, biggest mistakes are always going to be arithmetic in Calc 2. So let's see, we have a -6 plus 2 is a -4, so at least I can get rid of that. Actually, 3 will go into that twice, so that's 9 times 2 is 18, minus 6 minus 2/3 plus 2. That's 18 minus 6 is 12, plus 2 is 14, minus 2/3, and 30, 42 minus 2 is 40/3. All right, so, and I always run the risk of doing something wrong when I go that quickly, so you should probably not do math that quickly. not really showing you good habits. But anyhow, look how nice these integrals, definite integrals, are. The hardest thing is just the manipulation at the beginning to make sure you get it in a form where you can say, oh, I know the antiderivative, or I know what I would take the derivative of to arrive at that. All right, we are done with this video. There's still one more in this series called synthesis questions, and that will be kind of the higher end material that you'll often see at this point in calculus.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.